Welcome folks, and in today's video we're going to talk about something which I'm going to take right back to the ancient days of Egypt, and something that maybe Egyptian rulers might have been thinking about, a question which might have been on their mind, is how do I build these pyramid structures when the pyramid gets too high? So is there any sort of tools, physics tools, that I can use to make this possible? And so one of the tools that they came up with, so they're at this scenario where they've got a pyramid and they're wondering, what am I going to do here? They've got their pyramid here, and they're saying, well, I need to go a little bit higher. And so one of the things that they employed very cleverly was the use of a ramp. And the ramp in physics sometimes we call an incline. And an incline is nothing but a mechanical advantage, something which allows you to get, let's say, boulders, rock boulders, up a height a little bit easier than you otherwise would. So inclines are used just like pulleys and levers to give people a mechanical advantage, and we see them ramps and inclines in terms of our everyday life, in terms of wheelchairs, skateboards, and so on. And in today's lesson we're going to do one or two quick calculations and problem solvings related to inclines. So a typical incline problem that you may see might involve a skier. Let's call this skier Pat, and Pat is at the top of an incline, and on this incline normally it's shown from a side-on angle, a side-on view, and we have the incline is raised at this angle here, which is sometimes shown with the Greek symbol theta. And so you're asked, and you're trying to figure out, well, with what acceleration might Pat move down this slide? When does Pat start to move? And indeed, what are the forces that are acting on Pat? And so one thing that we can use to help us out here is we might want to get rid of Pat. Sorry, Pat. Okay, you're gone. And we might want to just use a simple representation of this scenario. So we go back to our FBDs, which we're looking at. The pink box represents Pat, and we're just going to firstly show the forces acting on an inclined plane problem. So the first things that we should say here is that we have FG pointing downwards in blue, and we have FN this time because it's always, remember, it's always going to be perpendicular to the surface. So in this case, FN is not directly upwards against FG, so it's off upwards to the left. Now, in these inclined plane problems, what we've got to do is we've got to break it up into its component values. So we might want to do that. And we know that there is a portion of that FG that's off to the right as diagonally as per the green. And then we also would know that there is another one that's here. In other words, we can make this a right angle triangle. And that's very useful because when we have a right angle triangle like here, we can start to use what we know about triangles to solve. So how are we going to figure out what each of these is? Well, in order to figure this out, luckily we have the magic of geometry to help us out here. And if we were to extend some of these drawings here, we would see that we have a right angled triangle if we extend that down, and we also have a right angled triangle in here, and we also know that these two lines here and here are parallel to one another. So we can use what we know about parallel lines and angles, and if we do that, we'd see that this angle here and this angle are actually equal. So now in these triangles, it's become a little bit obvious to us that two of the angles on each of the triangles are equal to each other, and so that means that the remaining angles here and here must also be equal. So if we know what this angle here is, let's say we know it's 30 degrees, then that means that the angle up in here, right here, is 30 degrees. And now we can just use trigonometry, and we can use, opposite, adjacent, and so on to figure things out, because usually we will be given FG. And so we can find what the green arrow and the red arrow is in terms of FG. So we're going to break this down into its components. It's important to say that. And when we break it into the components, we will see that FG parallel, I'm just going to write in what FG parallel means, and that's sometimes called the sliding force, and that is the force that's going this way, or in our old diagram it was going this way. That's actually equal to FG sine theta, sine of that angle, which earlier we said our angle was 30, but it could be any angle between 0 and 90 normally. And so that sliding force is equal to that. And the green one, FG perpendicular, which is this one here, is equal to FG cos theta. So we have we've a way to break these vectors into parallel and perpendicular components. And since there's no motion perpendicular to the slope, there is no motion perpendicular to the slope, then we know that the green and the orange arrows are equal to each other. And so very often, because we know that there's no acceleration up or down the slope, and what I mean by that is there's no acceleration perpendicular to the slope. So this object isn't accelerating up and down on this plane. It may be accelerating parallel to the slope, but not perpendicular. That means that this force and this force are equal. So that's another important thing that we should say about inclined planes. And so we get to this scenario here where Fn is equal to Fg cos theta. Now that is useful because if we need to get Ff, remember that's equal to mu Fn. And so that makes it equal to mu Fg cos theta. And so it actually means that it's equal to mu mg cos theta. So now we have a way of relating Ff to mu mg cos theta. If we know what mu is, m is, and we know what theta is, we can find that out. So let's look at an example problem. So a skier, maybe Pat, maybe somebody else, maybe Pat's back, who knows. But we have a skier, and that skier has begun to slide down a 30-degree hill. Determine the acceleration of the skier if the coefficient of friction is 0.1. So we have our skier in the diagram represented by the box. And what we need to do is we need to use what we've learned and break it into the x and y planes here. So the first thing that we should probably say is that in the y plane, there is no acceleration in the y-axis. So Pat, or the skier, is not moving up and down, so perpendicular to the axis. So what that means, of course, is that Fn is equal to Fg cos theta, as we already stated. And so Fn is equal to mu mg cos theta. And from that, we would be able to get Ff. So we could use that to get our Ff value, which is Ff is equal to mu mg cos theta. Mu mg cos theta. And when we do that, we see that the Ff value is 0.1 times whatever our Fn value is here. And the Fn value is just simply mg cos of 30, which is 382.3 newtons. And so our Ff value is 38.2 newtons. 38.2 newtons. And that's actually opposite the motion. So this is our Ff here, our force of friction. So if we want to find what the acceleration of the skier is, we're going to need more than that. So not only are we going to need the Ff value, but we're also going to need the F parallel, the sliding force, and that's on the x plane. So what we're going to have to do here is we know that we can use what we learned on the y plane, and we have our FF value on the X. So on the X plane here, we know that F parallel plus FF is equal to our net force. And from that, we can get our acceleration. Okay, so if we only know those. And so we remember that F parallel, the red arrow, the sliding force, is equal to mg sine theta. And we already know that this one here is going to be negative 38.2 newtons. And that's equal to ma. And it turns out that mg sine theta is 220.7 minus 38.2, and that's equal to 182.5. So you now know what the net force is, and that's equal to mass times acceleration. So if we want to know our acceleration value here, it's simply 182.5 newtons all over 45 kilograms. And that comes out in the wash as 4.05 meters per second squared. So that's a typical type of problem that you would get in an inclined plane that could be extended using kinematics to figure out the velocity once they reach the bottom, or how long it's going to take them to travel a certain distance or something like that. Another interesting kind of concept problem that you might get, I'm just going to run this video on screen, and when I lift this incline, you might be asked at what angle does this boat start to slide on screen. So when does that boat start to slide? At what angle does that happen? So that's another typical type of problem that you would get with inclined planes. So of course in that case we're trying to find the angle in here, the angle theta, with which it starts to slide. And because it's a cribbage board, I guess I get better put in some of these holes, some of these dot. That was giving me lots of friction here. Lots of friction, creating lots of friction. So we need to go back here before we go forward. So remember that force of static friction is overcome when the force down is equal to the force of friction. Okay, that's when that force pushing the green boat gets higher than that maximum force of static friction, then it starts to move. So if we put that into the context of our problem here, we know that the sliding force, our F parallel here, our sliding force, is equal to our backward force, which is FFS, and we know that that's equal to mu mg cos theta. And so it turns out that mg sine theta is equal to mu mg cos theta. So obviously the eagle-eyed amongst, the keen-eyed amongst you might realize that there's mg on both sides here. And so if we want to figure out the angle, we're almost there to figure out the angle that it begins to slide at. And if we simply just do a little bit of rearranging here, we'll see that mu is equal to sine theta over cos theta. And hopefully you folks know that in the sine and cos world that's equal to tan theta. So if we want to figure out what the angle that it starts to move at is, we just need to do an inverse tan on both sides here, and we'll get theta is equal to inverse tan of mu. So that's a typical type of problem you might get as well. So hopefully this video helped you to understand inclined planes. They're awesome power. We use them every day, and they will come up from time to time in typical physics problems. And the key is to break into those vectors, parallel and perpendicular vectors. So if you like this video, just give me a wee thumbs up and hit that subscribe button. Thank you.